If you haven't done so yet, make sure you pause the video and reread the problem before listening on. In part A, we need to find a formula for the gorilla population in terms of t based on this given differential equation. Now, you probably have noticed that this given differential equation is in the form of the so-called general logistic formula. So the textbook gives us the general solution to this general logistic formula. And so one option would be for us to compare the given equation to the general and then kind of plug the values in to get the solution. So for instance, if we look at the given equation, we have this decimal in front of p, and that's going to correspond to the value of k in front of p. So if you look very carefully, that little k right there, you'd be plugging in the 0.0004. In addition, the 250 is in the position of m, the so-called carrying capacity. So you could plug 250 in for m there as well as there, and then that would begin to give you the answer to part A. Now, admittedly, that works, but it doesn't necessarily teach us a lot about calculus. So in this video, we're going to actually take the given differential equation and we're going to solve it the old-fashioned way, using calculus, not by memorizing the equation for p given in the textbook. So that's our goal right now, is to solve this differential equation for p. And to do that, we're going to employ the technique of separation of variables. So what that means is that you're going to gather your p terms to the left side of the equation, and then you're going to gather your t term to the right side of the equation. And then once doing that, we will end up integrating. So to begin separating variables, we're going to multiply both sides of this equation by dt so that we can cancel the dt on the left-hand side. Next, we will divide both sides of the equation by this term p times 250 minus p. And by doing that, we're going to end up canceling that term on the right-hand side, just like that. So there you have it. We have successfully separated the variables. Once you've done that, what you're going to want to do is integrate both sides of the equation. Now, the right-hand integral is going to be very simple. It's the left-hand integral that's going to require some work, because in order to integrate the left-hand side, we kind of have to take an aside, and we have to take this rational expression and we have to rewrite it in terms of partial fractions. So this means that we put a constant a over the first factor in the denominator and then add that to the constant b over the second factor in the denominator. And our goal right now is to find the values of a and b. Once we have the values of a and b, then we end up integrating this expression, which is much easier to integrate than that expression. So our goal is to find a and b, and to do that, we're basically going to find a common denominator. So for this denominator, we're going to multiply both the denominator and the numerator by p. And then for the other one, we're going to multiply the denominator and the numerator by 250 minus p. Now, when doing that, you'll now notice that all of the denominators are common. They're all p times 250 minus p. So basically what that means is you can cancel out those denominators. And now all you have left in your equation is the numerators. So that's where we are, and we're going to be solving for the values of a and b. And to do that, we're going to begin by letting p equal 0. So everywhere you see a p in this equation, you're going to be filling in a 0. Over here, you're going to end up doing b times 0, which eliminates that term. And then you can see that you can just divide both sides by 250, and that's going to give you the value of a. So that was a neat little trick, and we can do something similar to find b by letting p equal 250. So everywhere in this equation you see a p, you're going to be plugging in a 250. And what's nice about that is you'll have 250 minus 250 here. That's going to eliminate that term. And then over here you have b times, again, 250. Divide both sides of the equation by 250, and you can see that the value of b is also 250. So now we go back to our original partial fraction decomposition, which is given right here. And for both of the values of a and b, we're going to be filling in 1 over 250. And in fact, because the numerators are an equivalent constant, we can factor out the 1 over 250, and that would give us 1 over p plus 1 over 250 minus p. So that's the final partial fraction decomposition. Now remember, this all started by us trying to integrate both sides of this equation. So we're going to go back to where we had left off right there. And for that term dp over p times 250 minus p, we're going to actually replace that with our partial fraction decomposition. So basically this, and integrating with respect to p, is going to be plugged in right there. And so there we have it. Now, in fact, on the left-hand side, we can factor out the 1 over 250. And now we're going to begin the process of integration. Now, the first integration is 1 over p with respect to p. So most of us know that that's going to be the natural log of p. As for the second one, we can do a bit of a shortcut for that, but we also might want to do a quick u substitution. So we can let u equal 250 minus p. We differentiate. We get du is equal to negative 1 dp, and then divide both sides by negative 1, and we have solved for dp. So now this second integration right here would become the integration of 1 over u. The dp becomes a negative du. You would factor out that negative, and so now you'd end up with negative natural log of u, but the u was 250 minus p. So this is negative natural log of 250 minus p. So that's how you could integrate that second integration, or that second integral. We'll kind of clean up our workspace here. And now we're going to move on to the right-hand side. That's a relatively simple integration because all we're doing is integrating a constant with respect to time. So that would be the constant multiplied by time, and then plus our constant of integration. Now we have to find that constant of integration in order to complete part A. And to do that, we go back and look at the initial condition given in the problem. So we were told that in 1970 there were 250 gorillas. This means that the population at time 0 is equal to 250. We can assume 1970 is a time of 0. So what we'll do is we'll plug in 250 for p and 0 for time. And my apologies, I may have just misspoken. I meant we're going to be plugging in 28 for p and 0 for time. And when we do that, we can see that here this term drops out. We punch the left side into our calculator. We get c is negative 0.00828 as the approximate value of c. So what we'll do is we'll plug in that value of c into the solution that we've been developing so far. Now what we're going to do is try to solve this for p, and we can begin to do that by multiplying both sides of this equation by 250, so we can cancel that over here. Notice you're going to have to distribute the 250 on the right-hand side. On the left-hand side, we'll use a property of logarithms in which we can take the difference of two logs and write that as the log of the quotient. So it's going to look like the following. Then to cancel out the natural log on the left side, we will raise e to both sides of the equation. The e and the natural log are inverses, so they cancel each other out. Over there on the right-hand side, we can use an exponent property to rewrite that right-hand side as the product of the two exponentials as follows. Then we could pick up our calculator and evaluate this term, which is about 0.126. So we have 0.126 times e to the 0.10t on the right side. Now, continuing our quest here to solve for p, we might wish to put this over 1. We could then sort of cross-multiply. So p times 1 is p. And then on this side, we're going to have the 0.126e to the 0.10t times the 250 minus p. We're going to end up distributing that exponential term. Now to both sides, we will add this term right here. And then what's kind of neat, on the left-hand side, we have that common factor of p. So this is sort of the moment of truth, because if we factor out the p, that gives us 1 plus this exponential term. And then we can, at long last, finish solving for p by dividing by that exponential term. So there it is. We've solved for p. Now, it might not look like the exact form we would have gotten had we just plugged into the solution given by the textbook, but we can actually make it look like that solution given by the textbook if we employ one final sort of maneuver here as I try to center this. There we go. So to make it look like the final form in the textbook, you're going to divide every term here by the 0.126e to the 0.10t. So we've done that, and somehow this has snuck in here on me. And in the numerator, the exponential term would cancel, and then you would divide 33.53 by that decimal of 0.126. And perhaps miraculously, when you do that, you're going to get a value of 250. You can verify that on a calculator. So that's going to be 250. Down here, this term is just going to equal a 1. And then over here, when you do 1 divided by that decimal, you get 7.929. That is over e to the 0.10t. That's fine, but if you bring that up to the numerator, you can write that as e to the negative 0.10t. And this is the final form that would match the one given by the textbook. So this is the correct solution to the differential equation. That is the answer to part A of the problem. We are now going to move on to part B, and in part B of the question, we are asked how long will it take for the gorilla population to reach the carrying capacity. Now, the carrying capacity is given by this value in the differential equation. They sometimes call that m in the textbook. So m would be 250, but it turns out if you actually plug in 250 in for the gorilla population, so if you plug in 250 right here, you would create an equation that would not be solvable. You would end up taking the natural log of 0, which doesn't exist. So we can't actually plug in 250 because the algebra wouldn't be functional. So what we're going to do is get as close to 250 as reasonably we can, and perhaps we can use 249.5. So we're going to plug in 249.5 in for the population because that's going to allow us to approximate the carrying capacity of 250. Now, how would we solve this? Well, we could recognize that 249.5 is over 1, so perhaps what we can do is just cross multiply. So if we did 249.5 multiplied by this denominator here, and then set that equal to 250 times 1. Next, we would divide both sides of the equation by the 249.5, so that on the right-hand side we get 1.002 approximately. Next, subtract 1 from both sides. Divide both sides by that 7.929. Take the natural log of both sides to cancel out the e. And then finally, you're going to divide both sides by that negative 0.10. And when you do that, you will find that the time is approximately 82.8 years, which we can round to 83 years. So it's going to take about 83 years for the population of animals to reach 249.5, which is approximately the carrying capacity of 250.